All right, take a look at these two triangles. I mean, they look pretty much the same, right? But here's the thing. In geometry, looks like just doesn't cut it. How can we prove with absolute 100% certainty that they are exact copies of each other? And get this, without having to measure every single side and every single angle. That's the puzzle we're going to crack today.
Okay, so let's dive right in. I want you to think of yourself as a kind of geometry detective. And to crack these cases, you don't need a magnifying glass. You need a very specific set of tools. So over the next few minutes, we're going to build out your geometric toolkit so you can prove without a shadow of a doubt when triangles are identical and when they're just, related.
The first and maybe the most important word for our investigation is congruence. Now, it sounds a little fancy, but it's really a simple idea. Just think identical twins. When two triangles are congruent, it means they are perfect, flawless copies. If you could pick one up and place it on top of the other, it would match perfectly. Every side, every angle, everything lines up exactly.
Now, before we even get to the tools, let's talk about the prize at the end of the mystery. There's this super powerful acronym in geometry, CPCTC. It stands for Corresponding Parts of Congruent Triangles are Congruent. And here's what that really means. Once you've proven two triangles are congruent, and we're about to show you exactly how to do that, you automatically win this huge bonus prize. You instantly know that all their other matching parts are also congruent. You don't have to prove it. This is the ultimate payoff, so keep it in your back pocket.
So, how do we get that payoff? How do we prove congruence? Well, the good news is you don't have to check all 6 parts of a triangle. 3 sides and 3 angles? No way. We've got shortcuts. So let's open up our Detective's Toolkit and check out the 5 essential tools that let us prove congruence with just a few key pieces of information. Our very first tool is side, 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 or SSS, and this one is just super intuitive. Think about it. If I give you 3 sticks of specific lengths, you can only build one possible triangle with them, right? It's rigid. So if you can show that all 3 pairs of corresponding sides in 2 triangles are equal, bam, the triangles have to be congruent. Case closed. Next up, we've got side angle side, or SAS, and with this one, the order of the letters is the biggest clue. See how the A is tucked between the 2 S's? That means you need 2 pairs of congruent sides, and the angle that's included between them also has to be congruent. That specific angle is absolutely crucial. It's like a hinge that locks the whole triangle into one single unchangeable shape and size.
Tool number 3 is kind of the mirror image of the last one, angle, side, angle, or ASA. Here you need 2 pairs of congruent angles, and you guessed it, the side that's included between them also has to be congruent. Once you lock in that side length and then fix the angles at both ends, well, there's only one possible place in the universe those other 2 sides can meet. It locks it in place again.
But what if the side isn't squeezed between the angles? Does that work? Well, that's where our 4th tool, angle, angle, side, or AAS, comes into play. And yes, it totally works. If you know 2 angles and a side that is not between them, you're still golden. And why? Well, it's a clever little trick. If you know 2 angles in a triangle, you automatically know the 3rd one, right? Because they all have to add up to 180 degrees. And that just turns this into an ASA problem. It's a fantastic shortcut. And finally, we have a special tool that's only for a specific situation, right triangles. It's called hypotenuse leg, or HL. So, step 1. You have to be sure you're dealing with 2 right triangles. Then, if you can prove their longest sides, the hypotenuses, are congruent, and just 1 pair of their corresponding legs are congruent, that's it. You're done. The triangles are guaranteed to be congruent. So here it is, our complete toolkit on one handy cheat sheet. We've got side, 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 angle, side, angle, side, angle, 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 side, and that special one for right triangles, hypotenuse leg. These are your 5 master keys to proving triangles are identical. Okay, so we've totally mastered identical twins. But what about scaled copies? Think about a photograph you love, and then a giant poster print of that same photo. They clearly have the exact same shape, but they're very different sizes. Well, in geometry, we have a name for that, similarity. Let's see how this is different. Let's be super clear about the difference here. Congruent triangles are those identical twins, same shape, same size. Their matching sides are equal. Similar triangles, on the other hand, are like scaled models, same shape but different sizes. Their matching sides aren't equal, they are proportional. This is key. The angles, though, the angles are still identical in both cases. Just like with congruence, we have some awesome shortcuts to prove similarity without checking every little part. And while there are a few, the one you'll use most often is way simpler than anything we've seen so far. It's just angle-angle, or AA.
And here's why the AA shortcut is so powerful. All you have to do is show that just two pairs of corresponding angles are the same. That's it. Why? Because we already know the three angles in any triangle have to add up to 180 degrees. So if two angles match up, the third one is forced to match as well. This guarantees they have the same shape, which means they must be similar.
So far, we've been looking at these shapes floating in space. But what happens when we pin them down on a grid? This opens up an incredibly powerful technique called a coordinate proof. This is where geometry meets algebra, and it gives us a whole new way to solve these puzzles. The big idea here is to actually place our shapes onto an XY coordinate plane. As soon as we do that, we can use tools from algebra, like the distance formula, to find side lengths, or the slope formula to prove things about the shape. It basically transforms a visual, abstract problem into a concrete numbers problem that we can solve. And this right here reveals the secret to making coordinate proofs easy. I mean, sure, you could just plop a triangle down randomly like the one on the right, but look at those coordinates. They'd be a nightmare to work with. The real pro move is what we see on the left, convenient placement. By locking a corner to the origin and putting a side right on an axis, you introduce a bunch of zeros into your coordinates, and that makes the algebra, so much simpler. This all boils down to a pretty clear 4-step strategy for setting yourself up for success. 1. Always try to use the origin, the point 0, 0, as one of your corners. 2. Place at least one side along the x or y axis. As we just saw, this gives you a whole bunch of zeros, which makes the math way easier. It's all about working smarter, not harder. So let's just pull this all together for a second. We've covered 3 massive ideas. We've seen how to prove shapes are absolutely identical through congruence, how to prove they're just scaled copies through similarity, and how to use algebra to do all of it using coordinate proofs. Remember, for congruence, we have those 5 core theorems in our toolkit. And for similarity, we have 3 key theorems, with AA being the superstar. So this is it. This is your brand new geometric toolkit. You can now tell the difference between what's identical and what's just a scaled copy. You know that the end goal of so many proofs is to use that awesome CPCTC shortcut, and you have the powerful new method of coordinate proofs to bring it all together. And that's really the big takeaway, isn't it? You've moved beyond just looking at shapes and kind of guessing. You now have the logical tools to prove, with cold, hard certainty, the true relationship between different shapes. And that leads to one final question. This way of thinking, looking for relationships, using evidence, building logical arguments, it isn't just for triangles on a page. From designing a building, to creating computer graphics, to making art, these principles are absolutely everywhere. So where else could this new toolkit help you reveal the hidden truths in the world around you?